All right, Honors Chem, today we are going to continue on learning about how to calculate enthalpy for different reactions. Today I'm going to introduce you to a version of Hess's law. There's two versions of Hess's law that we use. This one is systems of equations where we are adding different chemical reactions together to get the result of yet another chemical reaction. Okay, so Hess's law is what we call a state function. And that's important, and that's why we can use different reactions and add them together to get the full reaction for the reaction that we want to, the enthalpy for the reaction we want to, because it doesn't matter how we get that to that reaction, it just matters that we get to that reaction that we want to. Let me give you an explanation of that. So say I wanted to take the elevation change between here in Murray, Utah, to Park City, Utah. The elevation change between Murray and Park City is going to be the same regardless of how I get from Murray to Park City. I could go up Parley's Canyon, which is probably the easiest way to go up. Just go up I-80 and go up Parley's Canyon and get the elevation change there. Or I could take the long way and I could go down to Provo and go up Provo Canyon up through Heber and then go through Kimball Junction and go to Park City that way. That's a little bit longer. Or I could be really fancy and I could rent a helicopter and have somebody fly me up over the Wasatch Mountains from Murray to Park City and get to Park City that way. Now, regardless of how I got to Park City from Murray, that elevation change would be the same. It doesn't matter which pathway I took. My net change in elevation is going to be the same. And it's the same for these reactions. It doesn't matter which reactions I stack together, as long as I can stack them together in order to get to the reaction I want to measure. The sum of all those enthalpies of those various reactions will give me the enthalpy of the reaction I want. So let's give you an example of how this works. So suppose I want to be studying the formation of sulfur trioxide in the atmosphere. I would want to do that because sulfur trioxide is a very primary generator of acid rain because it binds with water in the atmosphere and creates acid rain. And I want to know why sulfur trioxide actually forms in the atmosphere. So I would want to determine sulfur plus oxygen is going to sulfur trioxide. I want to know the energy that is produced in that equation or that reaction so that I can understand physically, from a chemical standpoint, why that reaction is spontaneous, why that happens. And if I can figure that out, I can figure out maybe a way to alleviate some of the acid rain, okay? Unfortunately, laboratory experiments to produce sulfur trioxide to determine that delta H result in a mixture of products that is mostly sulfur dioxide. So sulfur dioxide is more prevalent. So how do I actually isolate the sulfur trioxide? In situations such as this, you can calculate delta H by using Hess's law of heat summation. So it's a summation. So Hess's law states that if you can add two or more thermochemical equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for that final reaction. It doesn't matter how I get there as long as I get there. And then I can add everything up together and that will give me the enthalpy. So I do have these two equations that I have the enthalpies for. So I have sulfur plus oxygen going to sulfur dioxide, and I know the enthalpy for that reaction. And I have sulfur oxide and sulfur dioxide and more oxygen going to sulfur trioxide, and I do have the enthalpy for that. So do you guys remember in algebra where you had a bunch of equations and you'd add them up and you'd figure out where those two lines intersect? Do you guys remember doing that? Well, this is kind of the same thing. We're trying to figure out, adding up a whole bunch of equations, where we can go with that. So do you guys remember at the equal sign, if you had things on opposite sides, you could cancel them out? Do you guys remember that in algebra? So, do you see some things that I can cancel out in this equation with this series? Do you see these two sulfur dioxides here? They are both on opposite sides of those reaction arrows, so I can cancel them out. Notice I canceled them out. So when I get down to what's left, I have 2 sulfurs plus 3 oxygens, giving me 2 sulfur trioxides. I just add the delta H's so that I get the delta H for the reaction I want. That's the reaction I wanted, isn't it? Right? So we're going to use these series of equations to get at the reaction I actually want, even if I can't do it in the lab. Okay? Thermochemical equations are usually written and balanced for 1 mole of the product. Okay, so here I have it for 2 moles. So I'm going to divide all of this by 2 to get at 1 mole of the product. Okay, so often we're going to have to then use fractional coefficients. You see how we use the fractional coefficients? For example, the thermochemical equation for the reaction between sulfur and oxygen to do 1 mole is where we're usually going for, is actually the following. So we're going to make everything down for 1 mole. Okay, so let's see how we use this in real life. Okay, so use thermochemical equations A and B. So we've got these 2 equations. We're going to try and generate this equation by using those 2 equations. We want to determine the delta H, or the enthalpy, for the decomposition of hydrogen peroxide, a compound that has many uses, and from bleaching hair, we use it to bleach a lot of things, to powering rocket engines. Okay, what I usually like to do is I like to look at what the reactants are. So I've got 2 hydrogen peroxides. So I'm going to look on these equations and try and find where hydrogen peroxide is. And if I look, I have it here. Now notice on this equation that we have here that the hydrogen peroxide is a product. It is not a reactant. So that means we're going to have to flip this reaction around. And notice also for hydrogen peroxide, up here I have 2 hydrogen peroxides, and here I just have 1. So not only am I going to have to flip this equation, I'm going to have to double it. Okay? So we're going to flip this equation, and we're going to double this equation, which also means that I am going to have to change this. When I flip this around, I'm going to have to change it to positive, and I'm going to have to multiply it by 2. Because if I remember, the reverse reaction is just the negative of the delta H. So I'm going to write this double, but I'm going to write it backwards. So I have 2 hydrogen peroxides going to give me 2 hydrogens and 2 oxygens. Okay? So if I do 188 times 2, that gives me a positive 376 kilojoules for that reaction. Okay? Now, the next thing that I'm going to look at is I've got water. So I need to look at where I have water here. I have 2 waters right here, and they're both on the product side, so I don't have to do anything to this equation. So I'm going to just write this equation the way it is. I've got 2 hydrogens and an oxygen giving me 2 waters. And that was a negative 572 kilojoules. Okay, so I'm going to add these 2 equations together, and I'm going to cancel out the things that I can cancel out that are repeated on both sides. Okay, so I've got 2 hydrogens on both sides, so those can be canceled out. Now here I've got 1 oxygen, and here I've got 2. I can cancel out 1 of those oxygens. So I'm going to cancel out one oxygen right there. So what I have left is I have, let's see, on the reactant side, I have the 2 hydrogen peroxides. And on the product side, I have 2 waters. And I have 1 oxygen. Okay? So that gives me, does that give me the equation that I wanted? It does. Now all I have to do is add up the delta H's. So I have positive 376 plus a negative 572, or I could just do the minus 572. And that gives me a delta H for this reaction of negative 196 kilojoules. Okay, so for this reaction, I have the delta H, or the enthalpy, coming in at negative 196. So I can create knowledge of that enthalpy of a reaction even though I don't necessarily run that reaction. I can sum up other reactions to get that. Okay, let's do another example. So I've got 2 carbon monoxides and 2 nitrogen monoxides going to make me 2 carbon dioxides and nitrogen. I want to know the enthalpy of the reaction. I'm going to use the following equations to do that. Now, let's see what I need to do. The first thing I'm going to do is I'm going to look at where there is carbon monoxide. Okay, so where do you see carbon monoxide? I see it right here, and there's 2 of them. So I don't have to reverse this equation because they're both reactants on both of these equations, and I don't have to double them. So I'm going to just write the equation the way it is. So I have carbon monoxides, 2 of them, plus oxygen, going to give me 2 carbon dioxides. Okay, and that is a negative 566.0 kilojoules. Okay, now the next thing, I have two nitrogen monoxides. And notice I have 2 nitrogen monoxides here. Now I am going to have to flip this equation because the nitrogen monoxide on this equation B is on the product side and not the reactant side. And I need it to be on the reactant side. So that means I'm going to have to flip that value of the delta H as well, or the enthalpy. I'm going to have to make that positive. So when I write this equation, I'm going to have 2 nitrogen monoxides going to give me nitrogen and oxygen, and I'm going to flip that value. So it's going to be positive 180.6 kilojoules. Okay, now let's add this up. What can we cancel out? I can cancel out the oxygens, right? So what do I have left? I have 2 carbon monoxides. I have 2 nitrogen monoxides. And I have 2 carbon dioxides. And I have 1 nitrogen. Okay, is that what I wanted? Does that match? Yes, it does. Okay, so let's add up negative 566 plus 180.6. That gives me, let's see, that gives me a negative 385.4 kilojoules. And yes, I can go all the way to the 10th because both of these values go to the 10th. Remember, when we add, we go to the nearest place value, or the least accurate place value, and that's the 10th in both of these cases. So I can get my delta H for that reaction. Okay, so let's look at this one. I've got, let's see, we're going to have to actually look at our table here. We've got nitrogen, or we've got sodium bicarbonate going to give us sodium carbonate and carbon dioxide and water. We're going to have to look at our equations and our tables for this. So the thing that we have to think about, everything that we have on our reactant side, we are going to have to deconstruct. So we're going to have to take this and deconstruct it to its elements. Okay? And I've got 2 of them. So let's deconstruct this to its elements. So I have 2 sodium bicarbonates. So if I deconstruct this to its elements, it's going to give me 2 sodiums and 1 hydrogen. Remember our Brinkelhoff elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine come in groups of 2 when they're elemental. So that hydrogen is H2, and we have, 2 carbons, and we have 2 times 3, so we have 6 oxygens, and oxygen is also, so we're going to have 3 oxygens. Okay, so there is our deconstruction of sodium bicarbonate. Now let's look at our table and let's find sodium bicarbonate. So if I look at this table and I find sodium bicarbonate, let's change this color. Actually, let's do this. Okay, so sodium bicarbonate. Here it is. I've got sodium bicarbonate. Now, this is the heat of formation. I just deconstructed it. So I'm going to have to flip that value of 950.8, and I'm going to have to double it because I have 2 sodium bicarbonates. So 950.8 times 2 gives me 1901.6, and it's going to be positive because I have deconstructed it instead of making it, okay, because those are heats of formation. So this is going to be a positive 1901.6 kilojoules because I had to multiply it by 2, and I also had to take the negative of it because I deconstructed it. Okay, so let's think about that really quick. Did I get the right one? Oh, nope, I didn't. I grabbed the sodium carbonate, not the sodium bicarbonate. So let's get that right value really quick. So if I look at the sodium bicarbonate, no, that is sodium bicarbonate. Okay, no, I got the right value. And yay, my computer's freezing again. So let's give this a minute. Maybe. Actually, I'm going to just make a new video.